Okay, now let's start to talk about drug clearance. Drug clearance means how drugs are eliminated from the body. And this lecture focuses on renal clearance. That means how drugs are eliminated from the body through the kidneys. And fundamentally, this is so renal clearance is a measure of the efficiency with which the kidney removes a drug from the plasma. And quantitatively, if you want to give a definition, so this is the definition. It's the volume of plasma that is completely cleared of the drug a unit of time. Now let's look at this diagram. This diagram explains the quantitative definition. What does it mean to the volume of plasma that is completely cleared of the drug in time? So this diagram represents a model. The model assumes that the drug is eliminated solely by renal excretion. So this diagram is a model. Just read a model assumption. You can release this assumption, have other types of models we will discuss in the next few lectures. But for this lecture, for renal clearance model, so this model assumption is very clear that the drug is eliminated solely by renal exclusion. So in this model, the body is basically divided by two parts, not the body, like the model only assume this part. So there's a body part where the drug exists, and the kidney part which filters the drug. So according to the diagram, in the drug, we consider that the concentration in the body is given by C total. So use the cytoplasmic, the plasma drug concentration as a representative of the drug concentration in the body. And then we give it a volume that's called V apparent. So we have seen that V apparent multiplied by C total would give you the total amount of the drug in the body at a given time. So now the drug is being eliminated by the kidney. If you see the diagram, when it is entering the kidney, it has concentration at C total, and then at a flow rate which is called Q renal. So Q renal is the renal plasma flow rate. So Q renal plasma flow rate. So plasma flows to the kidney at a certain rate, and this Q renal is describing that rate. So it enters the kidney with concentration of the drug C total and the volumetric flow rate Q renal. And then when it leaves the kidney and going back to the body, the drug has been cleared. So the C total becomes 0 and still with the same volume flow rate Q renal. So this is what it means, like renal clearance is the volume of plasma that is completely cleared of the drug. So the completely cleared of the drug is represented in the diagram that when it's going back, its C total equals to 0. So within that diagram, we can see that the solute removal rate by kidney is just the Q renal multiplied by C total. So that's the idea of this renal clearance. And we can write like a mass balance equation for the body. Basically, we are saying, okay, if you look at the body as a control volume, the rate change of the drug in the body should equal to the rate it's being removed. So that means the drug the A drug dt equals the rate being removed. So this is the accumulation. So we had an equation like accumulation equals to in minus out plus generation minus consumption. And this is the deaccumulation dt. And there's no in because we are modeling the body. We are not modeling the process of continuously taking drug or anything. So it's the process that the drug has already been taken, no new drugs moves into the body, then minus out. Okay, here is our minus out comes in, minus Q renal multiplied by C total. In the generation consumption, so because this model assumes that the drug is eliminated solely by renal excretion, so there will be no other consumption mechanisms. This is different if you consider other mechanisms of metabolism or other ways of removal clearance, then you may have other terms. But right now for this model, no, it's nothing else. It's just the kidney itself doing the job. So then this will be our governing equation. You can see this is this is the mass balance equation. Maybe it's not quite the governing equation. In order to make it the governing equation, we recall A drug equals to V apparent multiplied by C total. So our equation becomes, well, we assume our V apparent doesn't change. This is, we just assume the effective distribution of the drug in the body is the same. So we have V apparent. And with this assumption, V apparent multiplied by DC total dt equals to minus Q renal multiplied by C total. Okay, this is a differential equation in C total. And our goal is to obtain C total as a function of time. We want to know its time profile. And then we have initial condition because it's time derivative, the first order time derivative. So we need one initial condition, which is C total at t equal to 0 equals to C total not. So this is a symbol for the initial condition. So with this initial condition, and then with this differential equation, you can just integrate it once. You will get one constant of integration, and that constant of integration is determined by the initial condition. And you can just quickly get solve for C total. You can verify that, and you can solve it on your own. Just integrate it once. C total equals to, let's specify the function of time. So C total not the initial condition multiplied by exponent of minus renal divided by V apparent multiplied by t time. That's it. And this is showing that the concentration of the drug decays exponentially. And for practical reasons, people also define A renal as this ratio R renal divided by V apparent. So which we called renal elimination rate constant. So renal elimination rate constant. Okay, now if you do that, you can just simplify the notation a little bit of the temporal profile. We just have e to the minus a renal multiplied by t. That's essentially the same. It's just exponential decay with a different like symbol. So you may want to connect this theoretical model to experimental observations. Because in the experiment, sometimes people can also collect the data from urine. So consider the process by which like a drug appears in the urine. So we can say, okay, now let's connect the two. Connect to its related observations. Define Q urine as urine flow rate. We also define C urine as the concentration of the drug in the urine. So it's drug concentration. In the urine. Okay, so you can imagine that what's being eliminated or removed by the kidney should be the same as what you would measure from the urine. So that means like we would say that Q renal multiplied by C total. This is just a solute removal rate. Should be the same as the rate of drug appear in the urine. So this helps us to solve for Q renal. Renal is C urine divided by C total multiplied by Q urine. Why do we do that? Because Q renal is the rate of plasma going through the renal. It's not something you can measure easily, although you can always estimate. And then now people have very good estimation. But clinically, if you just ask a nurse saying, okay, what's the rate of the plasma going through the kidney? It's not something that the nurse can say, okay, let's measure it. It's not that case. But the nurse can say, okay, let's measure the drug concentration in the urine, such as C urine. And then let's take a blood sample to get a C total. And they can also estimate the urine flow rate Q based on the amount of urination versus the time. So these are something like measurable or you can estimate from experiment. And then you can use these to approximate what is Q renal. And that's a lot of like clinical setting. That's what's being done. So this is how you can connect to our discussion, the model for renal clearance, which give you the exponential decay, and the whole thing related to what can be measured from the urine. Okay, let me leave your homework problems. Okay, let's do two homework problems for this section. So the problem one is a drug with an apparent volume of distribution of this is eliminated only through renal clearance. So this is consistent with the assumption for today's lecture, the modeling. And it tells us the elimination rate, which is clearance rate. If the initial plasma concentration, plasma drug concentration is this one, determine the plasma concentration after 3 hours. The second problem is a drug is administered to a patient who produce urine at a rate of, it tells you the rate of urination. The concentration of the drug in the urine is given. How much of the drug is excreted in 5 hours? So the second problem is very practical. So it's almost like a clinical setting. Like if a person creates urine at this rate, and then after measuring the concentration of the drug in the urine, we can ask for this patient after 5 hours how much of the drug is excreted. Of course, this model has a lot of assumptions. For example, it assumes it's only eliminated by kidney, which isn't the case. It also assumes that the C total is the plasma drug concentration. Use it to represent the entire concentration in the body. So use it to represent everything given by V apparent. And the V apparent may not necessarily be the true volume of distribution, it's just apparent volume of distribution. So there's a bunch of assumptions. However, it still gives us some estimation that the people can refer to in a clinical setting. All right, that's all for this lecture.